Now we have Paulius. Paulius is a senior data scientist and ML engineer at Intellerts. He will share his thoughts on the pros and cons of AI-based tools and components and how organizations can benefit from HP data science workstations to support their MLOps processes. Thank you.
Well, thank you for the introduction. It's really nice to see you here this very shiny and very fine day. So, as I was introduced, I'm a machine learning engineer and data scientist at Intellerts company, and today I'll be talking about implementing MLOps process for health monitoring systems. So it will be like a practical talk, actually. I'll be sharing the experiences and challenges which we met while implementing the whole MLOps process for actual time series analysis-based system. Which gave some additional challenges and some additional thoughts for future implementations. So what I'll be talking about today, well, first I'll be talking a bit about what is MLOps actually. Well, I'm sure that most of you are more than familiar with this subject. So then later I'll be let's say, introducing or discussing several key components of MLOps-enabled systems. Again, those components are quite well known, and I think every ML engineer has at least implemented some of them. Then I'll move to the case study, which is the main subject in my presentation today, and a bit and a short discussion about the infrastructure that we actually used during our experimentation and might be considered for future experimental settings as well. So first, what is MLOps? So basically, it's nothing new. Actually, it's machine learning plus development operations. So I suppose all those technologies have existed before. We know that, again, machine learning is a very emerging area. Well, DevOps technologies are also well known, like Ansible, Terraform, infrastructure management. So these topics are quite familiar. But again, MLOps is kind of a subject which might include additional operations now. And even some specializations are very emerging, like DataOps, DevSecOps, which are dealing with security implementations, ModelOps, which require more extensive knowledge in model deployment, GitOps. Again, recently I've heard another term, which was FLOps, or Federated Learning Ops. So those are engineers who are trying to implement federated learning-based systems, which is very state-of-the-art systems, since I suppose there aren't a lot of people who actually are familiar with their development and implementations. But still, it's very innovative and highly emerging field. So although, as we see, those issues have existed long before. So MLOps is kind of at the intersection of all these issues. So this is basically, let's say, the whole picture of machine learning engineering. So we can see maybe three, let's say, main blocks, like data engineering, so exploration, validation, wrangling, then again monitoring, logging. So again, the whole model-based implementations. And naturally, again, deployment-based ones. So this is highly, again, related to all the development of MLOps-enabled systems, and this should be taken quite seriously. So these are, let's say, the core principles of MLOps philosophy. So these are the problems which are solved by applying MLOps. So we consider that as important as observability, monitoring, automation, continuous updates, reproducibility, deployment, scalability. So I'll talk a bit about each of these subjects later. Well, a bit shortly. Well, again, I'll try to touch the specifics of these issues which were met while during the development of our system. So again, there could be some additional components like feature stores, which are, let's say, required when you're developing machine learning-driven systems which that require feature-based engineering for for development of all the models of running them. So actually, again, it enables iterative and scalable feature-based development. Again, data code versioning, management of experiments and output artifacts. Again, we all know this is also a quite emerging field, and there are several even systems which are focused particularly on this issue, like MLflow, kubeflow. So then again, monitoring issues, deployment, serving. Again, these are the core problems. So now we'll start moving to those issues. So we have monitoring, which is ability to track and identify errors, root causes. So this is particularly important as we have to respond. The actions must be taken. So this is the action. This is ideally should be an actionable process. Again, we should monitor each component which is possible to monitor. For example, again, we should monitor the infrastructure state, the state of the developed system, the developed model. So this is kind of a process which can be enabled in multiple levels. And so we have a cycle like collecting, monitoring, responding, analyzing, evaluating, then collecting again. And so this is the process which is one of the core components there. Again, another problem, issue which should be highly addressed is automation. So automation, again, I think that every experienced DevOps would say that whatever cannot be automated will soon lead to additional problems while running the actual system, because, well, human errors are possible in such cases, and they may lead to some additional unexpected failures, which can be traced and handled quite difficultly. So again, this is relevant. What issues are relevant? So we can say that we need to collect all those data automation. So naturally, we know ETL process, automated data collection. Then again, data profiling, reporting. So this is also very important to ensure that the data that we're gathering meets certain requirements. Automated feature extraction selection as possible, automated experimental runs, automated evaluation, automated development. So ideally, everything that can be automated should be automated. And data engineer or data scientist or MLOps engineer should be, let's say, should be able to, let's say, confirm, monitor, and take actions whenever some unexpected problem or some unexpected failure happens. So then again, we have continuous model updates or continuous modeling. So again, we may face multiple issues, especially like drift detection, drifted data distribution, feature distribution, labels distribution, drifting data quality. Again, data quality, the level of data quality might be reduced, might just drop suddenly or unexpectedly. Again, drifting reality. So, well, it happens that the data doesn't represent the reality at all. So this also might be taken quite seriously. Again, the other issues, other questions or issues should be expected, like data sampling issues, data window selection, robustness to noise, and multiple other problems. Reproducibility is particularly the issue that I faced multiple times, especially during my career as a scientist. So again, this is an ability to run previous experiments in deterministic manner to obtain the same results, to reproduce the results which are provided in the papers, or let's say used somewhere else. We require the same outputs and results in previous runs, and to trace, let's say, the issues when we cannot reproduce them correctly. So again, failure to reproduce those results correctly may result in issues that are even more difficult to debug because we are not sure whether the problem happened due to the problems of implementation or just uncertainties which are not, let's say, discussed or described in the original papers or initial implementations. So there are several issues addressed as well, like random seeds. Are we handling randomness properly? Are we handling code versioning properly? Are we using the same data, the same experimental settings, the same library versions? So again, these are the issues which are addressed in the current state-of-the-art MLOps tools. Again, I consider this highly important for automated ML settings, as we have to deal particularly with the randomness factor here. Again, we may use like Bayesian optimization, genetic algorithms, which again they have some component of randomness there, and without taking care of it, you might again lead to quite, let's say, unproducible results. Again, then we have a deployment. Some deployment questions, again, load balancing, continuous process preferring recent changes, canary-based deployment. So again, we may not be able, let's say, to start the process on the whole population of the users. We may need to evaluate it particularly for let's say, a subset or sample of users, and then if everything goes as expected, we should move to the whole population. And naturally, additional optimizations which are related more to the engineering support, like batch inference support, especially in deep learning systems, to minimize the number of actual calls. So this is, again, the engineering optimizations which are dealt quite difficulty as well. So now finally, I'm moving to our case study, which was advertised here and which we'll be talking about. This is the system that we were implementing with the Health IQ. So this is a digital therapeutic company. Again, the main focus here is to enable healthcare providers to treat and manage some human issues like diabetes, cardiometabolic issues, COVID disease, which is very actual at this particular moment. So collecting the data. So as we can see, this is quite also a challenging problem due to quite multiple issues, which are quite difficult to trace. And actually, in practice, it took quite a lot of time just to identify them and to take actions to monitor and validate them. So again, we have several possible components here. So we have data collection from multiple devices, multiple wearables. The system performs various statistical and AI-driven analysis, emits particular signals which can be used as a digital alerting mechanisms, and some actions can be taken by the doctors, by the monitoring persons, or they can be, let's say, emitted to the patients. So I guess this is more of a context to understand how the system can be enabled here. So as I mentioned before, the system applies time series analytics and forecasting to measure and forecast the future state of a patient. So we're basically trying to identify whether the particular, let's say, type of the particular signal will decrease, increase, let's say whether it's blood pressure decrease or increase highly, or will stay stable. So again, this could be used as a monitoring and decision support system by the doctors. So now, why we consider this quite a challenging problem? This becomes a multidimensional problem because we're using multiple time series for inputs. Like pulse, respiratory rate, systolic temperature, SpO2. So again, this becomes a number of signals here as well. Then we have multiple models, as we're using ensemble-based modeling for more reliable results. So again, multiple time series models. Again, we have user dimension as modeling performed per user, and then we have time dimension as the model is refitted at each time step. So again, so we're moving now to practical issues, so monitoring data collection. So again, we have to monitor data quality, so we try to enable it using near real-time visual insights to detect drift whenever it happens, to collect and log issues as much as possible, and to handle missing data. So missing data handling is particularly important, and this is quite a complex case because we may have several unexpected issues that user does not wear any wearable, so user may be empty for some period, and again he starts wearing, then he stops wearing. So and that's why time series analysis becomes quite complex because you have to fill in the data, and it's quite difficult to understand what happened during the time gap. So the user wears a wearable, but it's not synchronized. Well, naturally, it can happen when people who are elder are wearing it, but didn't forget to turn it on, off. So the system fails to fetch data, so naturally it becomes discrepancy in data, time formats, provider data. So naturally, these are, let's say, more generic challenges which also should be handled. Well, model training is also quite sophisticated one, but again, we can handle it by using distributed learning, distributing based processing, using Airflow, which is quite scalable. So continuous training repeating, as I mentioned before, we're using an ensemble of univariate time series models at this moment. So we're applying our stable and fast implementations, which are let's say better. Currently, we're considered better as less established and slower Python ones, but naturally with improvements in Python, so we might consider them the future as well. Well, again, as I'll mention later, so R-based MLOps is also quite challenging because it doesn't provide so much infrastructural new things like Python-based infrastructure does. So again, and we have very strict requirements imposed by medical domains, so like interpretability. That's why usage of complex models is quite a complex one. So again, performing calculations of time, natural traceability, reproducibility, ensuring that we can evaluate each and reproduce the results at each time of step and know why the problem actually happened. So, as I mentioned before, so we have multiple models per user per iteration. Again, we may have additional dimensions as due to the nature of research and experimentation. Why does it happen? It's hard initially to decide what would be, let's say, the sliding window, or like training might be performed in 2 hours, predictions are calculated hourly. So again, we have this kind of dimension in uncertainty in parameter selection. Again, we have different window settings, as I mentioned. So basically, again, we may have additional dimensions when we're considering different settings in missing data handling. So almost every uncertainty may add additional dimension into such experimental settings and into such development of such systems. So, and again, naturally, one of the requirements might be to exclude some models if they don't perform well, which has already been seen, or to take too long to train. Basically, like Arima's implementation, which has, let's say, some automatic component to find these hyperparameters. It might take longer than expected, so sometimes it might be suitable to exclude it from the experiment. So storage and monitoring, as I said before, all the models must be stored for logging and backtesting purposes. To backtrack, ensure, to find everything, to identify the problems. Well, unfortunately, we have a high number of models, so this is quite a bit more challenging to just use existing systems. So we use internal model registry-like structure. Fortunately, we're able to serialize the models in JSON and store them in particular database. We can retrieve it and deserialize and retrieve them when required. So again, old models might be dropped in the future, but this is also consideration after more extensive testing of the system is performed. So again, storing data which was used to perform everything, so it's also a challenge. So as we can see, that monitoring which is everything is quite complex. This is like an example of dashboard, so which may contain like profiling information, like training time information, and quite a number of things. So that's why logging should be taken very carefully. And that's why we consider logging that we must log everything that we can. Forecast, performance, descriptives of the data, of original data, again, of the data that was, let's say, pre-processed and used as actual inputs for the model, various profiling information, data used, again, training exceptions to identify why did the model fitting failed, or some errors and inconsistencies happened, again. So that's why logging is based on, we're using custom logging implementations. Again, failure to perform fitting procedures does not happen very rarely, as we have issues with time consistency, length, for example. If we don't have any data, so naturally the model fitting might fail at some particular step because we don't have any history, or the part of the history is missing, or some other issues happened which are preventing us from performing the action successfully. So again, careful logging in cases when fitting could not be performed due to missing data, and ensemble aggregation adjustment when situations happen that, for example, some model fails to perform fitting. So, and there are alternatives which are considered later, but could be used later. So again, this is the practical, let's say, the tools that we're using. So this is nothing very interesting, unless this is particularly based on our language. So naturally, we have to take care of some environments that we're using, virtual environments that we're using like tools like Packrat, RN, and let's say, and deploying latest forecasting models using frameworks like Plumber. So in short, there are some R-based MLOps ecosystem challenges, which, well, let's say I found during the development, or during even previous developments, like limitations of the native workflow, orchestration, management tools. Unfortunately, R does not have tools like Airflow. Well, they have a nice framework called Targets, but unfortunately it doesn't, it's much less mature compared to Airflow, and it doesn't address quite a lot of issues which should be addressed. Then we have containerization issues, like, again, handling dependency management, some problems when we're trying to containerize it in an MLflow model store. But I suppose this might be addressed in the future by the developers. And naturally, so there might be some performance issues. Again, we have very fast time series implementations, but unfortunately, the R language, well, it's not as production, let's say, level as Python language. So this also might be addressed in the future, as after, let's say, time series analysis in Python becomes much more applicable and usable. Okay, so then 1 minute. In short, a bit about requirement infrastructure problems. So requesting a large number of users is quite costly. So this is particularly important for R&D phase. And the production level system includes only file development. So, well, it's naturally might be used in the cloud, but this is a problem when we're running with experimental phases. So in this case, we decided it was beneficial to invest into powerful workstations for experimentations, which are also enable GPU-based processing and GPU-based learning. So naturally, this is quite interesting when we're dealing with state-of-the-art models like transformers, recurrent neural network implementations, again, which, let's say, the capabilities which are offered by them. So basically, this is this was quite an interesting option here, and we consider it in the future for the development. And again, so these are the conclusions. I suppose I've discussed everything about it before. Like again, time series based MLOps is also quite challenging. It raises some additional challenges which are quite specific and must be handled properly. So I suppose that's about all. And thank you for your attention. I hope to hear some interesting questions.
Unfortunately, we don't have time for questions anymore.
So okay, so feel free to ask me about
afterwards. Okay. Thank you very much, Paulius. Oh.